Good morning. Our first talk this morning is Pascale Roesch from Université de Toulouse, who will speak on one-parameter families in the space of polynomials.
So first of all, I would like to thank the organizers, so Anna, Nuria, and all the staff here also. And so it's a really wonderful conference because I like really much parameter space. So immediately I was very happy, and I didn't imagine that it will be a so big conference. So thank you. And so the title is not very clear, but you will see. What is important on this slide is that it's a collaboration. Oops. Okay, with Hiroyuki Inu and Yan Kiwi. It's important for several reasons. The first one is that I think it's my fault because they are not here. Because okay, and this I will explain it next slide. Okay, and the second is that because Hiroyuki is making a lot of very nice picture. So this time you will see only three pictures from Arnaud. And this is the first one from Arnaud. So Pisa is a very nice place in summer, but this is also a very nice, in spring. This is also a very nice place. And this is the explanation why I think Jan and Hiroyuki are not here, because they came already to Europe in March. So, okay, so to finish this common work. So it's a project that started a long time ago and stopped at some moment. So maybe you guess it's also a nice place, but it was in winter. It's in Banff. Okay, so it's a long time ago. So I was taking the picture, so I was not on the picture. So, but you have the two collaborators which are here. Okay. Okay, and it's this project started after the work they have done, Hiroyuki and Jan together, about straightening, and also with looking at picture, at parameter slice picture. So we are in the space of polynomial. All this talk will be in the space of polynomial because it's really much more easy to work in polynomials. So sorry, Caroline. And then you know that you have this work of Douadi and Hubbard in an amazing paper, and of Lubitsch also, about Mandelbrot family that you can find in the parameter space. So you can see on this picture several Mandelbrot sets. And the question was to understand what are the other black region. So I will explain what is the color next, but I just wanted to explain the motivation. And this is a picture of the slice when one critical point in the cubic is of period 3, pair 3, 0. And it's much more complicated. You have a lot of different black region, not only Mandelbrot set. So now I explain a little bit what I will talk about. So as I said, I will stay in the space of polynomial of degree D, not only cubic. And I take critically marked monic centered polynomials, meaning that I want to parameterize the space by the critical point. So I have a fixed big degree D. And so I have D minus 1 critical point, because 1 is at infinity, which is of degree D. And I fix, I ask to the polynomial to be center, so the sum of the critical value, critical point is 0, and B is a value at 0, just to fix something. So it means that your map, you look at it as looking at the critical point in the space and the value of 0. So you can compute the formula by integrating the derivative and putting sum plus b, okay? And so starting from the cubic, okay, we wanted to extend this. So this is a project that starts with the cubic and wanted to extend it to other families. And so we decided to have only a slide of dimension 1. So we want to have a unique critical point which is moving the slice. So it's a free critical point, but not only a free critical point. What we want is to have a free critical orbit. So what is, and then we want to define a slice with this. So explain. What is a free critical point? A free critical point is a critical point which has infinite orbits. And we ask that there is no critical point in the forward orbit of the critical point. So you can have critical point in the backward orbit, but not in the forward orbit. So you can have several critical points, and the free one is the last one, but it's not exactly like this. So you can have 2 critical points which are free, and they belong to the same ground orbit. So the ground orbit is, so you have a critical point, and you have all the points coming after some iteration. Okay, so you can have a critical point here and critical point here. So these 2 critical points are free if they have infinite orbit. Okay, and so you have 2 free critical points and 1 ground orbit. Okay, so I should define what is a free critical orbit. So free critical orbit is when you have exactly 1 ground orbit that contain a free critical point. So you can have several free critical points, yes, but only 1 ground orbit containing all these free critical points. So I give some example in the cubic. So this map is monic centered, and the critical points are A and minus A. And if you take this value for B, then you get that the critical point A is fixed. So it's not free. And then minus A is a free critical point. So you have only 1 free critical orbit. If you take plus 2A here, then what you get is that the critical point A is mapped to the preimage so minus A and the 2A have the same image. So it's a co-critical point of minus A. They are both mapped to the same critical value. So it's a picture like this. So you have only 1 free ground orbit. So we start with a polynomial like this, and we define the slice following this orbit. And for this, we need to look at the critical orbit relation, which is defined by the other one, because there are several critical points. Only one is giving you a free ground orbit. So it means that the other one are either with finite orbit, okay? So there is a relation, like one is mapped to a fixed point or something like this. And all the other critical points, they belong to the same ground orbit. So it means that you have a relation between all of them in this grand orbit. Like here, I don't know, in the example, you had GA square of A is equal to GA of minus A. Okay, the orbit of the critical point is not finite, but you have a relation like this, which relates all the critical point in the slice. Okay, so we start with one polynomial with one critical free orbit. And this is what I explained you. So there exists a relation. And if you have a relation between two critical points, so you have d minus one critical point. If you take any two critical points, and if you have a relation between them, then you want to take all the map F in the space of polynomial of degree D, which satisfies the same relation. Okay. So this is called a critical orbit relation. And of course, we don't know if it's irreducible. So we take the irreducible component of this set, okay, that contain F naught. Okay, so you can prove using a result of transversality that it's smooth at this parameter F naught. And in all the connectedness locus, you can prove this. So you can look at this, it's well defined. The core curve, which is the irreducible component, is well defined. I don't want to enter in this. This is the context. And so the simplest example are the slice in the cubic, which are the slice where one critical point is of multiplier 0. Critical point, sorry, is of period n. Exactly n. So you have this formula for the polynomial, and you ask that you have a period n point. And so Mathieu Arfeux and Yann Kiwi, they proved that this slice per n0 are irreducible. So it's a really core slice. And also, I want to emphasize that we are looking at this curve because they are important in the sense that they contain a lot of post-critically finite map. And so we are interested in this black part, which contain a lot of hyperbolic components. So we want to start with hyperbolic polynomials, but not only hyperbolic polynomials. We want to have relative hyperbolic polynomials. So we want to have something which is close to PCF, post-critically finite. So this is in the space of cubic polynomials. So if you want to look at an irreducible curve in the set of cubic polynomial, then you have this classification due to Charles and Thomas. I made a mistake. Louder. Okay. Okay. Thank you. So the idea was just to emphasize that these are the important curve to look at if you want to have a lot of post-critically finite. So one of the two critical points is persistently preperiodic. So this gives you a relation like per n0, or there is a persistent collision. So like this collision is persistent in the slice. And the last case is when you have, oh, sorry. Oops. When you have symmetries. So I don't want to speak about this. Okay. So there are many questions on these core curves. I don't want to enter all of them. Question of smoothness, of irreducibility, genus, and punctures a lot. And I will not be able to cite all the people working on this, so I'm sorry. I cite some of them. And what I want to emphasize that the slices that are I think the most studied for the moment are the slice where you have iterate L of some critical point, which is mapped to a period N point. And there's others, but these are well studied by Milnor, Bonifant, Epstein, Bufkor, and Mathieu Arfeux, and Kiwi. And Laura also, and a lot of people. So I just want to mention that you can look at the same question, but it's really much more difficult in space of quadratic rational maps. So Caroline made a very nice talk about this. So we are not looking at this question of genus and things like this. What you want to understand is the connectedness locus in the core curve. And the connectedness locus is this black region. This is a picture in a pair 1, 0. So one critical point is fixed. And here you have a picture of pair 2, 0. So you have one critical point of period 2 in the cubic slice. So what is the definition? It's not a black region. It's definition is that it's a relative connectedness locus because we take all the map in this slice, this core curve, such that the field Julia set is connected. The Julia set is connected. In fact, it's the intersection of the connectedness locus with the slice in this case. So in case you have one critical point which is prefixed, you get this picture, which is not so much familiar, I think. I don't know. Okay. So what I want to say is that in this slice, you have the center of the component, for instance, and you have other several points which are have a dynamical behavior which is different. So the critical point, the three critical points at these centers can be seen as not free, okay? But this is free outside the countable state, which are the center of the component. And we can say, because it's not free, how can you continue this to follow this? But because we parameterize by the critical point, and because we have a critical orbit relation, you know what it means to follow with by the parameter the free critical orbit, the free critical point. So you can assume that the free critical point that you choose is of degree D, so it corresponds to the D first critical point. Okay. So since we have, we can have a critical point which is fixed or prefixed in this slice. So we cannot speak about hyperbolic parameters. So it will be relative hyperbolic parameters. So, sorry. We say that we have a relative hyperbolic parameter if the free critical point is in the basin of an attracting cycle. So it's a particular case of stable component. And so you can prove that using Milnor results, for instance, or quasi-conform deformation, that for each relative hyperbolic component in this core curve, there is a unique PCF, postcritially finite polynomial that we call the center. Okay, so you can see many relative hyperbolic components in this slice. So you have, this is a fundamental domain, so there is not all the rest of the picture. So this is in the cubic slice. So you have a critical point, which is mapped in after two steps to a fixed point. And in this slice, you have a critical point A is mapped after one step in a period 2 attracting cycle at the center. Okay. So if you look in this component, the critical point is in the basin of attraction of an attracting cycle. So you can follow this attracting cycle. So I called it O of F. Okay. And when you go to the center at F stars, what happens is that the free critical point collides with a point in the preimage of this cycle, attracting cycle. So we add some assumption because otherwise it's a little complicated to state the results. So we add some assumption on the center. First, we consider only periodic cycle. So the critical point is in the basin, immediate basin of an attracting cycle. Also, we ask that there is no new relation induced on the critical point than the one coming from the collision of this critical point with the cycle. So it means that when you collide with a cycle, of course, you have all the relation induced by the forward orbit of the map. So every critical point which are in the preimage, they are not concerned with this relation. Okay. Okay. And we also ask that if you take the Fatu component containing the free critical point, there is no post-critical point in its closure, except, of course, the free critical point. Okay, otherwise it's a little more complicated to state the results. Okay, and when we have a collision like this, we associate a type to the map. Okay, so if you have a collision with a periodic orbit, which is not post-critical, so it means it's not in the orbit of a critical point, meaning the attracting point is not in the orbit of another critical point in the cycle. So it's only attracting. Then the model is you will have something which is unique critical of degree D, where D is the degree of the critical point which collides. If you have a collision with a critical point, so maybe I should make a picture. So you have a cycle like this. And so the critical point is in the basin and is going to collide with this cycle. And the first case, there is no critical point in this cycle, okay, before to collide. And the second case, this one is a critical point. But the other one are not critical. Okay, there is no other critical point in the orbits. So this one is critical of degree d prime. This one is critical of degree d. And this is called A, like for adjacent. And the next case, you have a collision with a critical point here. I mean, this one is not critical, but the critical point is in the orbit of the cycle. So this one is of degree d prime, so from here to here. And this one is of degree d from here to here. Maybe I should add some more components. Okay, so the return, so you can have several critical points. So maybe I have 2 critical points. And then the degree d prime is a combination of all the degree. And the last type is when you have both critical point here, critical point. This is of degree d prime, and this is of degree d second. So it means that the free critical point will collide with a critical point of degree d prime. So like in the case A adjacent, okay? So you have 2 critical points in the same phi2 component that collide. And then in the cycle, you will have a lot of critical points, maybe. You know that there is a critical orbit relation. So they have to be at the center of the phi2 component. And the total degree is d second. So we call them like this to remember that U is unicritical and A is adjacent, and it's a composition of them, a succession of things like this. Okay. So I want to emphasize that we cannot have more collision with critical points in the backward image with this cycle, okay? Because we ask not to have this, because then you can deal with it, but it's a little more technical. You have to cut space, parameter space, something like this. So I don't want to speak about this. So these are the only possible case of collision with this cycle. You cannot have a collision with a preimage and someone which is in the cycle, because we ask to have a regular center. And then, so these are the type of the centers that you see on the slides. And now we will associate a model family, like Mandelbrot set is a type U2. You collide a critical point with an attracting point, and the model is the Mandelbrot set, the quadratic family, Z squared plus C. And what you see in the parameter space is the Mandelbrot set. So we are 4 family. So I call with a poly of D when you have a unicritical polynomial of degree D. So the model UD, as I said, you have only one critical point of degree D that collide with an attracting cycle. So when you renormalize, you get a map of degree D to the same phi2 component. So what you get is a ZD plus C, and the model of the connectedness locus is a multibrod set. This is a degree 4, I think. and the second model family. So you have two parameters. I mean, you have 2 degree, d and d prime. You have two critical points, one of degree d and one of degree d prime. So the formula is this one. You have to integrate and you have some parameter. So it's a one parameter family. Because what you want is that the critical point. So maybe I have to start again because all the models are on the same picture. So the A dd prime, you have one critical point of degree d prime and one critical point of degree d, and they collide. So, and then they make a tour, and then they come back. So when you normalize, okay, what you get is a map with this point, which is fixed, of the same degree d prime, and a point of degree d, critical point of degree d colliding. So it's an adjacent case. So you ask that the critical point in the model is fixed. The critical point of degree d prime is fixed. And the model in the cubic is just the connectedness locus is a black and white picture, the complement of the red. D and d prime are equal to 2. And the third and fourth model, for this I have to introduce generalized polynomials. So you take a couple of, it's a fiber over 2 points, in fact, a couple of polynomial of degree d and d prime. So it's not unique critical, okay? And they act on, so it's fibered over 2 copy of C. So F, take a point in the first copy C naught and map it to C1, and G, take a point in C1 and map it in C naught. Okay, so this is a notion of generalized polynomial introduced by Milnor and Jan and Hiroyuki and several people. I don't know. Okay, and so you look at the Julia set. So you have a Julia set in each fibers. So you have 2 Julia sets. It's not connected because you have 2 fibers, but you say it's connected if and only if the 2 fiber Julia sets are connected. So we can define the third model using this generalized polynomial. So you take unique critical polynomial of degree d and of degree d prime, and you ask that the critical point of g of degree d prime, that is the question, is periodic of period 2. So maybe I explain why. Yes, you're right. Yes, it's fixed by the composition. Okay, I didn't write it, but okay. Yes, exactly. So you have d prime, which is here. And when you collide with the center, what you get is that when you iterate, so this is like G, and this is F. So the return map is a composition of this map, which has the omega prime of degree d prime, and this map, which has a critical point at the center of degree d. And when they collide, you have a period 2, F composed with G. So you have, for the composition, you have a fixed point. So when you write the composition, you have a 1 parameter family because of this relation. And for example, oh, sorry. For instance, when you take d and d prime equal to 2, so you get this family quadratic family, z square plus a, that you compose with another quadratic family, so z square plus c, but since the critical point has to be fixed, so 0 is mapped to a square, so you have to take minus a square. So this way you get clearly a one parameter family. And the connectedness locus is this picture. So it's a degree 4 because the composition of 2 degree 2. And it corresponds that to have both Julia set connected in each fiber. The fourth model, the most complicated. So you have a collision with, we have already a critical point here of degree. So this is omega prime of degree d prime. This is your omega coming to the cycle. And then you have several critical points. Okay. Critical point. And the return map, it's not return, but map going back to the component containing the critical points, it has degree. This is second. So you pass through several critical points, but each one is mapped to next critical point. So it stays unicritical. And then when they collide, you compose with a unicritical. Okay, so this is d plus d prime. Okay. So you have, as before, the composition of G and F, and the point omega prime, because we assume it's, I mean, we consider all this for the return map as only one critical point of degree so it's this second. Okay. Okay, so the critical point omega prime has to be mapped to the critical point of G. Okay, the critical point of F has to map to the critical point of G and to come back here. So this gives you a one parameter family. And the formula is this composition of F and G. So here you have 0 and A as critical point. So A is a parameter. Okay. So now I have to, so these are the model. And now we have to find, to go from the parameter space to the model. And in the work of Douady-Hubbard, you need to find a neighborhood of the small Julia sets and proper map, holomorphic proper map of some degree to a biggest one, biggest open set. And so we have to do this starting from the center of the hyperbolic component. So this is the work that was done by Hiroyuki and Yan Kiwi. They defined a lamination associated to the center. So what is a rational lamination? So you have this external rays because it's post-critically finite. You have this external rays landing to the Julia set. And if you consider only the external rays in the rational set, then you can define it for every polynomial. And you can consider all the map F having the same pattern of lamination. So it means that you consider for instance, in the Mandelbrot set, so there is no cusp here, sorry. You know that in this part here, you always have 1/3 and 2/3, and all the preimages that lands together in all this domain. Okay, so this is a rational lamination associated to this center. Okay, so we take the center, we take the rational lamination of the center, and consider, so they define, Hiroyuki and Yan, they define the connectedness locus relative to this lamination. It corresponds to all the map F which contain this lamination. So it means that you add more connection. It means that you will tune, sorry, you will tune with some other Julia sets inside. So this is potentially renormalizable, because it means that if you add lamination, you tune with something. So this is combinatory, in the combinatorial way, tuning. Okay. And so, of course, all the hyperbolic component is contained in this combinatorial renormalizable set. And if I take this center, so what you get here is a copy of the Mandelbrot set attached at this parameter. Okay, so this is the result with that we were finishing in March in Toulouse. You recognize Toulouse. If we start with a hyperbolic center, and under the hypothesis I gave you, so periodic, regular, and no critical point on the boundary of the Fatu component containing the free critical one, then the set of renormalizable, combinatorially renormalizable map is in fact renormalizable, and it's homomorphic to the connectedness locus. So I should have had dynamical. Okay, because otherwise, sorry, it has no meaning. To the combinatorial, to the connectedness locus of the family of the model, which I gave you, corresponding to the type of the center. Okay, so this is what you see on the picture, in fact. Okay. And this is in progress. So using this result, we can get that the boundary of the relative hyperbolic component are Jordan curve, because in the model, you can pass it to the slice. So here I show you maybe the model. This one, I think it's here. And I turn it so that you can see exactly the unique critical of degree. So this is this part here that you recognize here. It's a U2, okay? And this one is taken here. So I turn it so that you can recognize, no, it was not U2, it was adjacent A2. It was adjacent, sorry, A22. So this one, so you start with F star here, and then this part here is a combinatorially renormalizable set for this center. And you see that you have a nice Mandelbrot set, and here you have to take care to get this 2-1. So this is a composition of two quadratics. It's U2, U2. So this is only for the slice per 2, 0. And if you look in the slice per 3, 0, then maybe you see here, this small one. Maybe it's not this one, it's another one, but this is a zoom, and you recognize A2. And so here it's the center picture. So here there is no problem to find the little Mandelbrot set. Okay, so it corresponds to a primitive case. The center is a primitive, meaning that the fatu components are disjoint. Okay, and here so the same as before, but in pair 3. And so it's much more complicated to find example which are not in pair n0. So it took a long time. And so in this case, you have the critical point A, which is following the critical point minus A. Minus A is 3. So you have to look here. And in fact, minus A is colliding with attracting cycle. So you get U4. And it's not possible to find the other model in these slices. So this is a degree 4 polynomial with 2 critical points forming a cycle of period 2. And the 3 critical point is coming. So you know that you will have the last example, which is the more difficult to find, which is AU. And this is a type AU. Okay. I didn't put the picture next. Oh, it's too bad. So here also it's difficult. You have to look which Mandelbrot copy you have to take. Okay, you have to cut. Of course, you know that not. I surround a place where not everybody is in the connectness locus because I cannot cut what is with my pencil. Okay, is it okay? So I want to add some comment. So Wei Xiao Shen and Yiming Wang, sorry, they recently proved a very similar result. So, but they have assumption that the polynomial you start with is hyperbolic, so f star is hyperbolic, and also that it's a primitive. So it means that the fatu component, they don't touch. The fatu component, which is capturing the critical point. And also Yiming Wang also had a result in non-hyperbolic case, but with also technical assumptions that I don't want to write. It's a little long, so it's not all the cases. And also I consider only the periodic case because the capture case is a little different. And there is a result from Zhishao, Wang and Yin, okay. And they prove that if you have a capture hyperbolic component, then it's homomorphic to the sphere, the real sphere of degree 1 less. So Yishao is here. You can see his poster maybe tomorrow, I don't know when. And also concerning the Jordan curve, Xiaoyang Wang proves that in the cubic, the slice parent 0, the hyperbolic component of Jordan boundary. Oh, sorry. So in all these cases, the method is different. I mean, they use quasi-conformal surgery. So they use some, so you will see tomorrow if he has a poster. It's algebraic things. And he used puzzle, I mean, a rigidity. Okay, so in our work, the difference between what has been done here, it has been done since Banff, so it's a long story. And we have F star, which can be not hyperbolic because we restrict to core curve. And also we can have critical points, which are preperiodic in the Julia set. But we had this assumption that the critical points are far from the fat2 component containing the free critical one, okay? Because otherwise you have to cut past and it's a little complicated. And also, as you saw, we have satellite renormalization in pair 3 and pair 2. I show you. You have to connect the good Mandelbrot set at the good place. So it's a, oops, sorry, I have to stop. I don't know. Maybe I give you quickly sketch of proof. Or... Okay. So the sketch of proof is the following. So we prove that the combinatorially renormalizable set is a closed set. And this follows from the continuity of the landing of the rational race, continuity with F. So you can see maybe Said will speak about this tomorrow. Okay, okay. So it follows from Karsten and Said results in periodic case at least. Okay. So then, as in the work of Hiroyuki and Jan, you have to define a polynomial of given type to prove that you can renormalize it. And for this, you have to choose a marking for the polynomial like of a given type. Okay. And then you can prove that this is renormalizable and that you get a straightening map from this renormalizable to the connectedness locus of the family. Okay. So these are the renormalizable map. The renormalizable mean polynomial-like of type T. So they already prove that it's injective and onto over the hyperbolic, so relative hyperbolic. Okay, the proof is the same. And so the goal is to extend to all the combinatorially renormalizable set. So using the tubing, you can extend it locally over every point except the parabolic point, as you have seen the small copies. The parabolic point such that the zero rays in the renormalization is parabolic. And you have only two such things, okay? Because in this model, you have two unique critical. And so you prove that it's topologically holomorphic of degree 1. As the next step, it's to prove that it's proper. So you have to deal with dynamical. So this is a parameter conference. So you have to do with the dynamical situation of this parabolic point and point at the boundary. And the last thing is to glue back this parabolic point to recognize which one go to which place. Okay, and then you get a nomomorphism. I just want to add advertisement if I am allowed to. So I was speaking about core curves. So it was critical orbit relation. And the next step is to understand what is going on when you have a parabolic or a Ziegel in the slice. So starting with the cubics, as before, we start with the cubics. So you don't have infinitely many post-critically finite, as Charles proved in this slice, but you can always speak about relative things. So in this slice, you have, so Runzezang proves that when you have a persistent parabolic point, the relative stability of the locus contain more than a copy of connectedness locus. You have also copy of the field Julia set, so copy in a certain sense of the corresponding parabolic, quadratic parabolic. So he will have a poster tomorrow, so you can ask him. And this is the same for Ziegel parameter of bonded type. You can have stable components which are corresponding to the critical point being tracked by the Ziegel component. So this is a common work with Young-Hooks. Drach also speak about this already. And just to continue advertisement. So this is parabolic case, which is the next step before Ziegel. So this is a ongoing project with Luna. So you have to guess which one is parabolic. And thank you for your attention. Sorry for the delay.
So on the pictures, it's very easy to spot when you have a copy of the Mandelbrot set,
Yes.
but the other three things, I have
Yes.
difficulties
No,
distinguishing them.
You cannot distinguish because they look the same, I mean. And you have to know exactly, here you know that you have a critical point which is in the basin of another critical point or thing like this. And, oh, sorry. It's very difficult to find where is the copy, just looking at the picture. But and what you have to add here, so this is an adjacent case. So you have to add this Mandelbrot copy to this part. And you have to, there are one Mandelbrot, one, and one, so it's 5. And you have to cut all this. So it's not evident to see. Yeah.
Thanks, Pascal. Do you have any notion of like decorations off of any of these CF stars? Like, is there any way that you can like?
So this is a decoration, for instance.
Yeah, and do you have any like way of like combinatorially predicting these guys, or?
So that they should be captures of. There are a lot of captures, and I didn't talk to this, but there may be some limbs going out of this connectness locus and plenty of things, yes.
Okay, thanks.
But
any other questions? Okay, let's thank our speaker once more. All right, welcome back. Our next speaker is Han Peters from the University of Amsterdam, who is talking about equilibrium measure for transcendental functions.
That's it. Does this work? Yes. Thank you. And thank you very much for the organizers. It's wonderful to be here. One of the organizers is my co-author, Anna Miriam. I'm very glad for this collaboration. It gives me the chance to be here. So Miriam is here. Leandro just arrived in time to hear a talk about his own work. John Eric is not here, but I imagine many of you will know him. And our bigger project started 10 years ago already in 2014, when Miriam had the bright idea to combine our fields of interest, to combine transcendental dynamics with dynamics in several variables, which was more the expertise of Leandro, John Eric, and myself. And well, transcendental maps, so non-rational maps in higher dimensions, there are a lot of them. There are already too many rational maps, you could say. So you should look at some specific families, and we decided to look at maps ZW goes to, and then f of z minus delta w comma z. And you may know this formula. It's the formula for a complex Hanon map, where for a complex Hanon map, this is a polynomial, but for us, this is a transcendental function. And this is, well, a much more restrictive class of maps than just arbitrary entire maps, for which you likely can't say that much in generality. So we started looking at these, and our first results were results like there exist periodic points, there exist escaping points, results that probably you can't prove for arbitrary entire maps. So both Miriam and I gave talks about it, and Nassim Sibouni was in the audience, and he gave us an exercise. Namely, he asked us prove that the entropy of transcendental functions is always infinite. And it turned out he gave that exercise also about 15 years earlier to his then PhD student, Romain Duchardin. And Romain worked on it, and We're still working on it. It's a difficult exercise. So I won't be quoting any theorems from Romain, but he had several insights in his thesis that do play a role also in the work I'll be talking about today. Let me go back to rational functions first. So I'll discuss some very classical results that you know, but I have to start with this. So we know that for any rational function, the topological entropy equals the log of the degree of the function. And so Misiorewicz and Pesitsky proved the lower bound, and then Gromov proved the upper bound. The first result in much more generality. Gromov's result really used holomorphic mappings. Also works in arbitrary dimensional projective spaces. And this result was generalized also for complex Hanon maps, for example, by Smiley. You get the log of the algebraic degree, not the topological degree, which is 1 for these maps. And then Brolin, Lubitsch, and many others afterwards proved that there exists a unique measure of maximal entropy. This will be my focus during this talk, obtaining a result like this for transcendental functions. This result has also been generalized to higher dimensions for anamorphism of projective space by Furness and Sibony, for complex Hanon maps by Bedford, Lubitsch, Smiley, and there are more difficult classes of maps for which this result has always also been obtained. Now, for the topological entropy, we started working on this. So Nassim suggested we prove it for two-dimensional maps. So we asked Miriam, so what's the proof in one dimension? But it turned out nobody knew. So we proved it. But then Walter Bergweiler remembered that Marcus Wendt also proved this result in his PhD thesis a number of years ago, with a very different proof. So every transcendental function has infinite topological entropy, which I think is what you would expect. And the good news about Wendt's proof was that, so our proof was really very naive, looking at estimates for the hyperbolic metric. Wendt's proof, to my mind, is much more sophisticated. And that proof, the ideas of that proof, we could use in 2 dimensions. So the result also holds for transcendental Hanon maps. Now, the questions I want to look at today is, does there always exist an ergodic measure of infinite entropy? Is this measure unique? And is the support of this measure equal to, can it be equal to the Julia set? Is it always equal to the Julia set if there are more measures? Now, I realize that I haven't told you what entropy is. Many of you will know, but I made a movie. Arno is not the only one who can make movies. Let's see. But now I cannot find it. Here it is. Here it is. Entropy video. So these are 2 actors showing you. This is a stop motion movie. So you have 2 kinds of currents, chocolate and vanilla. And if you pour that into a bowl, then if you turn it around, nothing happens. But then when you stir, it becomes light brown. And look, the result. And I don't know what happened there. Saved by the traffic cone. Let's see how to go back. The PDF here. And then also this one. Okay, thank you. So there are many notions of entropy, and I already mentioned topological entropy, measurable entropy, or metric entropy, sometimes called measure theoretic entropy. The entropy of a Markov chain will play a role in this talk. I won't define them all, but entropy measures how quickly the two kinds of currents mix up. Right. So in physics, it's an entropy of a state. At the end, you have a higher entropy than at the beginning, but we're looking at the dynamical systems, and it's the rate at which you stir the two colors. You could say the rate at which orbits that start very near each other go far apart and may come back to each other. Now I'm not able to go to the next door. Next. Yeah. Yes, thanks. So let's look back at this theorem of Lubitsch, and the existence of the measure of maximal entropy may not be the most interesting about this fact, but also the way you construct this measure, to my mind, is one of the most fundamental ideas in complex dynamics. You take a point and you put some mass at it, and then you pull it back, and you equidistribute the mass over the preimages. And in the limit, you obtain the measure of maximal entropy. And Charles talked about doing this with forms, and you can talk about equidistribution of periodic points. There are many ways to obtain the same measure. Can we do this for transcendental functions? So immediately you notice that there is a problem here, because typically a point has infinitely many preimages. And if we have a mass 1, we cannot distribute this evenly over the preimages. So maybe the part equi doesn't make sense. We have to assign weights to the preimages. We have to put some mass at the preimages and some fewer mass at some other preimages. So, but even though maybe the word is wrong, I will still call it equidistribution. And so I'll present some examples where we're able to do this, but it seems really difficult to do this for arbitrary transcendental functions. You have to decide for every single point how you want to distribute the weight of the preimages, and then it has to give you convergence. How do you do that? So we have, for each W, we have a probability vector V, and with the VI's corresponding to the ZI's, so the pullback of a Dirac mass is just the sum of VI times the Dirac mass at the preimage ZI. And we repeat this, and hopefully that converges to a measure of maximal entropy. And there are many, many ways to decide upon this probability vector. So maybe there are also more possible measures. So there are other ways to define the measure of maximal entropy. At least for polynomials, you could do it via a potential, the Green's function, and take the complex Laplacian of that. So here's a picture of the potential. You could do equidistribution, it's the same function. There's a third way, at least for this particular one. This is one where you have a Cantor set. So here, for this very simple quadratic polynomial, you have symbolic dynamics. You have shift maps sigma here, well, sigma, shifting sequences of zeros and ones, and then there's a homeomorphism between that space of sequences and the Julia set. So if you can find a measure on the space of sequences, then you can push it down to the Julia set. So how can you get measures up there? Well, you can consider a Markov chain on two states. So it depends on two probabilities, P and Q. And then you find a stationary measure whenever you take P and Q in the open interval. And the stationary measure induces an invariant measure on the space of sequences. So in this case, the maximal entropy, log 2, is obtained only when you take a smart choice. You take P is Q equals 1/2, and then the stationary measure, of course, gives mass 1/2 to both 0 and 1. Yes, I know. So the stationary measure gives mass to the 2 points 0 and 1. And it's, so here we have, on the Markov chain, we don't have a deterministic dynamical system, right? They're probabilities, and this measure is, sometimes people call it invariant, but it's invariant under the probabilities. But you can get a deterministic dynamical system by looking at the space of sequences, and then, well, you look at cylinder sets. So you take a finite tuple y, and you look at all sequences that, for example, here start with that tuple y. So you have y0, y1, y2, up to yn minus 1, if it's length n. And then the probability that you start with that vector is the probability that you start with y0. So that's the stationary, that the stationary measure gives you that, times the probability that you go from y0 to y1, times the probability that you go from y1 to y2, etc. So the transition probabilities and the stationary measure gives you the invariant measure of all cylinder sets. And if you, in the very simplest case, when P and Q are equal to 1/2, then the mass of any cylinder set for an n tuple is just 1/2 to the n. But if you choose different P and Qs, you get products of P's and 1 minus P's, etc. So now let's look at these probabilities. So Pij is really the probability that you're at state j at time n plus 1, given that you're at state I at time n. So we can also go back. So we can look at the probability that you were at state I, given that you are now at state j. And then by Bayes' theorem, you can express that in terms of the Pij's, and S is my stationary measure. So S has the mass of the points 0 and 1. So we get the transition probabilities for an inverse Markov chain. It's the same Markov chain, except that the arrows are pointing in the opposite direction. And it tells you, well, if I'm now at this point, what's the chance that before that I was at point J? Or no, I'm now at point J. What's the chance that I was at point I one step back? So using these weights, we can get the equidistribution. So this works for any Q and P, but we have different weights for the pre-images. So this is exactly when we have transcendental dynamics, it will be more difficult. We'll have infinitely many states. But this is an idea that also works for polynomial dynamics. So let's look at a slightly less trivial polynomial. So here is a degree 3 polynomial built up using two polynomial-like maps, one of degree 1 and one of degree 2. And I take a point and I think, okay, I had to find the measure of maximal entropy by taking 1/2 and 1/2. So let's do that again. I'll take a chance is 1/2 that I came from this point, and it's also 1/2 that I came from that polynomial map. So I'll give these both mass 1/4. That's of course not going to be the maximal entropy, but you can do this. And then you could make an even less trivial polynomial. So here you still have degree 3, but then here I make something of degree 4 by adding some other component that's mapped properly to the big disk. So this is a very simple schematic for a degree 4 polynomial. But then I would like to define these weights for any point. But as I move this point outside here, these 3 points, they become 3 points here. And I I can't say anymore which point corresponds to this one and which one corresponds to that one, because if I turn around a critical value, these points perturb. So I could say, well, okay, then here I have to give them all the same weight. And then there's another point there, I'll give them the rest of the weight. So I can do this, but now you're seeing that choosing the weights is not so easy, and there's a lot of freedom, but I cannot do it in a constant way. I cannot let the weights depend constantly on my point W, right? So imagine that I have a transcendental function, and these are also the transcendental maps that, one of the transcendental maps that Romain Dujardin looked at in his thesis. Imagine that I have a transcendental function, which is really a polynomial-like map at infinitely many scales. So I try to sketch something here. I have a blue scale with a blue Julia set here, but then at a larger scale, I may have some higher degree map. I get some larger Julia set here that contains my blue Julia set. And then at some much larger scale that doesn't fit on the board, I get the orange Julia set, but this happens infinitely many times. That must be one of the most simple transcendental functions, right? So perhaps for these maps, we can guess what the weight should be, and then equidistribution works. So these maps I will call transcendental functions that are polynomial-like maps of every degree. So quickly, the definition of a polynomial-like maps, you have two topological disks, one inside the other, and then you have a proper holomorphic function of some finite degree mapping the smaller one to the bigger one. That's a polynomial-like map of degree D. Then what's the most typical example is a polynomial, the simplest example. So take any polynomial of degree at least 2, then if you choose a large disk, dr around 0, say, and you look at its preimage, it's contained inside of this disk, you call that U, and then the restriction to U, the map from F from U to V, is polynomial-like of degree D, for any choice of R large enough. Okay, so now imagine you have a transcendental function, and you let the coefficients shrink extremely fast, all non-zero, let's say, and once you have chosen A0 and A1, you choose A2 so that it hardly influences the behavior on the polynomial-like map that you've constructed for your previous degree. But at a much larger scale, you get a degree 2 polynomial-like map, and you continue defining the coefficients recursively like that. Then you obtain a transcendental function that's polynomial-like of every single degree. And also you can play with the time scales. It can take arbitrarily long until you switch to the next degree, which can be convenient. So I call any function of this form, I call polynomial-like of every degree. Yes, they're nested. So the V's are all disks centered at 0 of radii that, in my picture, I showed multiple at the same screen, but that shouldn't be possible. They're at completely different scales. Okay? Sigma proper. Okay. So now for these maps, so these may seem like very simple maps. For any polynomial-like map, you have a measure of maximal entropy, whose support is the Julia set of that restriction. Then it follows immediately that the topological entropy is at least log D for every single degree D, so the topological degree is infinite. It's usually one doesn't define, well, usually one defines topological entropy on compact spaces, so you have to choose a definition of topological entropy on all of C. There are many definitions, but for any definition that I've seen, it will be infinite. And then you could say, well, let me just use all of these measures simultaneously. I'll just take a sum. I'll take half of the first one and a quarter times the second one and an eighth. That will give me an invariant probability measure, and it will have infinite entropy. But this measure is, of course, not ergodic. You can't build an ergodic measure by taking sums of different invariant measures. If you just look at the support of the measure mu2, so that's Julia set 2, and you look at everything that lands in there, that's completely invariant, yet its measure is a half, so it's not 0, 1. So that's not an ergodic measure. So you need to do something different than just the most naive idea. It turns out these maps, sigma proper maps, are not that simple. For example, the critical points can still go out and come back, and you can have any kinds of periodic points. You can have any kind of polynomial dynamics. So it's not that simple. Bishop, when he constructed transcendental functions whose Julia set as house of dimension 1, he considered examples of these maps that are more restrictive. He made sure that all critical points just go off to infinity. So that makes the dynamics much, much simpler. And we'll call these maps Bishop maps. And they can also be constructed, but you have to be more careful. You can define a sequence of annulus where each annulus covers the next annulus. And then but now you have to time the coefficients A and it's not sufficient to have them just get small fast enough. You have to time them precisely so that your next annulus you have to jump over the critical points. The critical points have to lie in between these annuli, and then if you're in between two annuli, you jump over the annuli and again, and you go off to infinity. So then what Bishop showed is you get some Cantor set of circles, and these circles you can show they're smooth, and you can get estimates, and he proved that you can get house of dimension 1. That is not so relevant for what we're doing now. In fact, we only learned of Bishop's result that he used the same maps afterwards. I think it's quite natural because these must be the simplest transcendental functions, right? No, the Julia set is unbounded. Unbounded, yes. Because so what's this big circle? It's a circle that goes into the next annulus and in the next. It's like the middle of these circles. So the forward images of these circles, they go off to infinity. But then you can get pre-images of these circles back in, no, the other way around. Pre-images of this big blue circle, they can go be arbitrarily far away, and you can pull them back and they become the smaller circles. So there's a very clear combinatorial picture of all these circles. And that combinatorial picture, that helps us to construct the measure. So this is the idea of the annulus covering annuli. So here I have a nice round annulus. And for these pictures, I took honest polynomials, not transcendental functions. So here I have, on the left, I have a degree 5 example, and on the right, a degree 6 example. And I looked, I pull back the next annulus into this annulus. So here, in the brighter colors, there is the inverse image of the next annulus with the same modulus. And what are these black lines? I took a polynomial with positive real coefficients. So I know that on the positive real axis, I go off to infinity. And these black curves are the curves that are mapped onto the positive real axis. So you see here, you have a degree 5 covering of the next annulus, right? Each of these pieces here is mapped 1-to-1 onto the next annulus minus the black, the positive real axis. And on the right, I have a degree 6 example. So you have many, many of these annuli, but then you switch the degree. You go from, for example, degree 5 to degree 6. So in that case, it looks slightly different. depending on the parity, but you also get a disk here, and I exaggerated the disk because it's really so small that you can't see it. There's a disk there that's mapped back onto your very first disk. So the blue is not the picture is honest except for the blue disk, which I enlarged. But there is a piece of curve either on the left or on the right. So this happens when you switch degrees, making sure that the critical point does not lie in this annulus. The critical point lies slightly inside here. So in total, what you get is you get a whole lot of maps where you have a degree 2 polynomial-like map. So you have an annulus here, which is mapped to an annulus, which is mapped to an annulus with a twofold covering every time. But then you switch. That's when you jump over a critical point by timing your A3 precisely, and you become a degree 3 polynomial-like map. But then also you can go back to your original disk, your annulus 0. And then you continue with degree 3 until you jump over another critical point, and then you can also go back or continue with the degree 4 map, etc. So that gives us a nice symbolic dynamical system. So what are the states? They are the subsets of the annuli, right? So this annuli divided into D sets that univalently cover the next one. So here I have my 2 starting subsets of the very first annulus, and I only drew 1 arrow here, but really this one goes to that one, but also to this one. And this one goes to the next 2. And you continue like this, so every time there are 4 arrows here, until you jump over the critical point, and then you get 3 states. But the green arrow comes from only one of the states. Only one of these states contains a disk that is mapped back to the original disk. And then you can, again, so here there are 9 arrows, but I'm just representing that with this arrow. Here you continue arbitrarily long until you go to degree 4, etc. So it's more complicated than the Markov chain on those 2 states, but it's still something that you can hope to assign transition probabilities to. There's a lot of structure in here. So the question is, how can we define the transition probabilities here on this directed graph in order to obtain an ergodic measure of infinite entropy? So what you do is you assign the transition probabilities by first stating, well, what's the measure I want to get? You do it the other way. So you say, okay, I want this set that I wanted to have mass a half. And then this set, I wanted to have mass C2, and this I want to have mass C3. And then you say, well, here I want it to mix as much as possible, because we want to have large entropy. So if we have a state here, I want to have a half and a half. Everywhere I want to here I have 1/3, 1/3, 1/3. Unless, so if you have that, you have no freedom except for the green arrows. So it turns out that the masses determine the probabilities for the green arrows. And there's also what goes further here. Okay, so the masses that you want, your stationary measure, right? This is the measure on the states. It's not a deterministic dynamical system, but a probabilistic. The stationary measure that you want determines, if you make some uniformity assumptions, it determines the transition probabilities. And then, okay, that's what I wrote here. And then I claim that, well, first of all, for any choice of C's, C2, C3, so any choice of the masses, adding up to 1, of course, you get an ergodic Markov chain. So you obtain an ergodic measure. And then you can compute, or you can estimate the entropy. It has to be summable, But it turns out that if you multiply by each mass by log n, then that has to sum up to infinity. So can you do that? Well, an example is 1 over n log n squared. It's summable, but if you remove the squared, then it's no longer summable. Then you get infinity. So that's an example of masses for which you get an ergodic measure, which has infinite entropy. And the entropy for a Markov chain is much easier to compute because the entropy of the deterministic system is actually the entropy rate of the Markov chain. Now, it turns out that you don't have full support for this choice because there were more arrows. I ignored this point. But from this state, you don't only go back, you go, the image of this cell actually covers all of these cells in the complex plane. But so the probability, the transition probabilities were all 0 for these red arrows. Okay, not a problem. And so anytime you go back, you actually in the complex plane, you cover all previous annuli one-to-one. So what you do is you have some Markov chain, it's aperiodic, it's irreducible, and it's positively recurrent, meaning that the expected return time from any state to here, the state 0, is finite. Then, and take any red arrow that was 0, for any Markov chain, you can make it slightly positive. If you make it small enough and reduce the other arrows slightly, then it's still positively recurrent. So it's still ergodic. You still obtain a stationary measure. So, and you can do that for all arrows or for any collection of arrows. You can make them positive. Just one by one, if you like. You make this one positive, and then having done that, you make that one positive, small enough. So once you've made all transition probabilities positive, or all transition probabilities that correspond to the dynamics of your complex map, then you obtain full support. So then the support of the measure equals the Julia set, which was that Cantor set of this unbounded Cantor set of circles. Yeah. Okay, that I've already said. So the conclusion is that there's a lot of freedom. I said take your masses roughly 1 over n log n squared. If you have something that sums up to 2, and you change the numbers a little bit, you make them slightly smaller, it's not 2 anymore. But if you have something that sums up to infinity and you change the number slightly, it's still going to be infinity if you do it if your change is not too large. Any finite number of numbers you can change. So they're infinite, and for the measure on your space of sequences depends uniquely on your transition probability. So if you change those, you get a different measure. So there are infinitely many distinct ergodic measures for which you have infinite entropy, and the support can be equal to the Julia set, as we argued on the previous slide. But 2 slides ago, we found one for which the support is smaller than the Julia set. They're all living on the Julia set, but it can be a proper subset. And then I claim that the statements holds for, we think, so any theorem I'm presenting here has a question mark behind it. Let me use that terminology from a previous talk. But we think this is correct. So if you take a disjoint type map, let's say finite order, maybe another assumption, then you get the same statements. You have infinitely many measures of infinite entropy, and the support can be everything, or it can be a proper subset. So here is some exponential map with a Baker domain. Here's the sine of z over 2 with an attracting basin. For these maps, you have these Cantor bouquets of curves. The endpoints are dense in the Julia set, and there is a symbolic representation of these endpoints. So for any endpoint, you can view them as elements in, well, infinitely many states to the power n. So that's a huge space. It's much larger than our directed graph that we had previously. But it contains that directed graph, right? So we can put in the Markov chain we had previously into this set. Then we don't get full measure, but there are only countably many possible arrows between points in a countable set to points in a countable set. So each of them we can then make slightly positive, and then you obtain full measure. Okay, so this bishop map was, to my mind, the simplest example of a transcendental function. And there it was very clear what the symbolic dynamics is. Here that the symbolic dynamics is, you get much more orbits, but it contains the orbits that you have, the symbolic orbits that you have for the bishop map, and then you can perturb to get the full Julia set. Now, I started talking about these maps where the coefficient decreases sufficiently fast. I claim that there also exists an ergodic measure of infinite entropy for these maps. But here I don't know how to get a symbolic representation. This can contain any polynomial behavior that you like. So, but it looks a bit like the bishop map. It looks a bit like the bishop map, except that for the bishop map, these disks at different scales, they line up exactly. And here they may not lie. You have some degree 2 map, and that's you have some other circle for a degree 3 map. You can't expect that this circle maps exactly onto that. But if you make them shrink sufficiently fast, it looks a lot like the bishop maps. So what you can do is you can construct a bishop map with the same number of steps. So you have degree 2 map for a very long number of steps, then a degree 3 map for a very long number of steps, etc. That's fixed. And now we take a bishop map with the same number of steps. I'm cheating a little bit because for the bishop map, this number of steps is exact. But for these maps, you could have points for which it takes 1,000,000 steps and some other points where it takes 1,000,001 steps to get to the next degree. So but you can approximate the map by a bishop map. And for that bishop map, we have the weights. As I talked about, the Markov chain, so far I didn't need the weights because we had the Markov chain. We didn't need equidistribution yet. But if you have the Markov chain, then you get these inverse probabilities, Qij, or I call them Qji, I think, the weights for going back. But then what we do is we say, okay, let's use exactly these weights. And the way we constructed them, they don't depend much on the point. They only depend on, you have 2 points, in which degree regime are they? So we define these different degree regimes and we say, okay, if you have a point in this degree regime 5, then you have 5 preimages. We'll all give them these weights. So we give them the weights that come from the Markov chain. So from the bishop map. So the bishop map really functions here as an inspiration for choosing the weights. Then we want to prove that with this choice of weights, you get equidistribution. But for that, we have to look at the proof of Misha's theorem. So let me go back to Ljubich's result. So what does Ljubich do? You look at some operator AF, and it acts on continuous functions on the sphere. by by pulling back onto the map F. And then Misha proves. And is this due to you, or was this already due to Fatou, or this idea is? Aha, okay. Okay. So there was some idea there. Okay. So you take a point and you take a small disk around W and you pull back this disks. You may encounter critical points for some, but let's say the point W itself is not a forward image of a critical point, then we could take a tiny disk so that almost all preimages at every scale are univalent branches. And then it turns out the diameter of those, you get a normal family. So the diameter shrinks to 0 for these. Oh, that is what to do. Okay. So you use this to prove that given a phi, so phi is continuous on the sphere, so it's uniformly continuous, then this sequence is equicontinuous. So you have these, and this is nice when you do the rational dynamics, all the weights are the same. So you have these different inverse branches. They're almost all the inverse branches. They're very small, so your phi varies arbitrarily little on these disks. So what you get is equicontinuity for this family of pullbacks, and you show that the eigenvectors are really with eigenvector 1, which is the only unitary eigenvector. They're exactly the constant functions and nothing else. And then the conclusion of this is that these pullbacks of phi, they converge to a constant function, namely just the integral of your unique measure over phi. Okay, so this a one slide presentation of that proof. Now, how do we do it for transcendental functions? We already know how to define the AF, but we have to define it with weights. So we have infinitely many preimages and we deal with weights. And they vary with the base point. We cannot keep them constant. So that's an issue when you have an inverse branches and it lands in places where the weights for going back further, when they are not constant, then as you go back further, your weights of these inverse branches depends on the point in that disk. So how can you deal with that? Well, first you make sure that the weights vary smoothly, and secondly, you prove that inverse branches, in fact, shrink exponentially fast. So how do you prove that? So here's a stronger version of this shrinkage. In fact, you look again at your family of univalent inverse branches, then the diameter of most inverse branches converges to 0 exponentially fast. So how do you, and here most is not all univalent inverse branches. There may be, for example, you could start out in a Siegel domain, like an invariant Siegel domain, take a little disk in there. Then there's that disk keeps rotating around. But its weight goes to 0. And most other inverse images get into smaller and smaller pre-periodic components. So how do you prove that they converge to 0 exponentially fast? Well, you consider first, you throw out all the non-univalent branches. We could make sure, as Misha's proof, that they have arbitrarily small mass. Then by shrinking the disk, you get bounded distortion. But if you have bounded distortion, then that gives you a relationship between diameter and area. Now, the total area of the sphere is finite. So, and then you count how many branches are there. Well, the number of branches still grows exponentially fast. If you look at different inverse branches for the same n, they have disjoint, pairwise disjoint. So the number of branches that are fairly large, that must be small. So you take some exponentially fast, you let it be at a lower rate than your degree, then you get to throw out only a small number of inverse branches with large area, and that large area gives you small area gives you small diameter. Now it turns out that this stronger step 2, it still holds for the transcendental functions that we're considering. So we have exponential shrinking inverse branches, and we've smoothened the way the weights vary with the point W. So now if it's possible that inverse branches land in this area where the weights vary with the point, but they shrink exponentially fast. So if you start with a small enough disk, your weights will vary arbitrarily little over this disk, even going back very far. And as a result, you still get equicontinuity of the pullbacks of the maps, also for the transcendental functions. You have to do some calculation. You have infinitely many critical points now. So you still have to argue, you have to know where they are and argue that, well, most inverse branches, which is now not in terms of counting them, but in terms of their weights, most inverse branches don't encounter critical points, right? So there's some analysis there, but this is the idea. So that's what I want to present for now. Of course, we hope to get some results for arbitrary transcendental functions, but to be honest, we have no idea. Maybe Miriam or Leandro has an idea, but I have no idea how to do this. Then we would like to prove results for transcendental Hanon maps. I think we know how to get measures of maximal entropy, but the problem is that we don't know whether the support of this measure equals the Julia set, and that's a very famous problem also for polynomial Hanon maps. Is the support of the measure of maximal entropy equal to the Julia set in terms of the non-normality, both forward and backwards? That's an issue. If you'd like, I could say more about that proof, but for now, let me stop here. Thank you very much.
Questions?
Results. So you weigh most pre-images homogeneously and then somehow put on the rest some decaying weights. So what is the kind of
how do we define the weights?
Yeah, how to formulate equidistributed? What is equidistributed? So with respect to your.
So for each point W, we look at all its pre-images. There are infinitely many, and we assign weights to all of them, adding up to 1.
But
and all of them get positive weights.
Is there some rule that you can say that it is somehow a function which is a kind of roughly constant or something? So that for most pre-images it is.
It depends on where your base point. Maybe if I go back to the Markov chain. So the inspiration comes from this Markov chain. So this gives you transition probabilities for the forward dynamics, and those transition probabilities also give you transition probabilities for the backwards dynamics. So if we have a point here, then there are infinitely many pre-images, 2 in here, because from the beginning it's 2 to 1. 1 in here, but it will have a much smaller mass, because the mass, this mass C2 of this enormous number of points is small. So only very little should go here. Then there's another preimage here, and that should get an even smaller amount of mass.
So mass depends on how far the point is.
Yes, yes. You need to, for the forward dynamics, you need to let this go to 0. Yeah, you need to make sure that your expected return time is finite.
And can you translate this result to some equidistribution result for periodic points, orbits points?
That's a good question. I don't know yet. Yeah, that makes a lot of sense to for any periodic point, you know, you're staying in a bounded degree regime. So it should be on that degree bound, it should be possible to assign a weight, but we haven't considered it yet. Yeah, thanks for that question.
And our last speaker of this morning is Dierk Schleicher from Aix-Marseille Université, who will speak on combinatorics and core entropy of transcendental entire functions.
Okay, thank you very much for bringing us all here together. It's always a place full of inspiration and good contacts. I'm very happy to be here to meet all of you. And yes, so the question mark is the title Transcendental wasn't the title, and this will be the second half of the talk, but I will start with some discussions on the polynomial story. So therefore, but I didn't want to extend it much further. It will be transcendental, but not only. So what will I do? It's a bit of boring overview. It's in some sense a good connection to the previous talk by Han, and one of his results will also be mentioned. Topological entropy for, well, polynomial and later for transcendental one-dimensional maps only. So then mainly in the first half or so, I will talk about polynomials, for which we meanwhile know quite a bit. But the story is much more complicated for transcendental entire functions, which you can also mention, which you also learned in the previous talk. So much of this is based on work with Malte Hassler, who is currently a PhD student in Cornell. So unfortunately, I don't have as nice a video on entropy as we have. I don't have any video at all, but this is, yes. After this, if I had one, I would be embarrassed because it would be hard to live up to the previous one. So I start with the same result as before, but I start with a different reference. And so the beginning of the story is indeed the result. The topological entropy for one-dimensional rational maps is always the log of the degree. And yes, my understanding is that this was independent work by 2 people who at the time were not aware of the other. So I do justice by mentioning the other person who did this independently in his master thesis, and learning message to all the students here: publish your results. So master student Misha dutifully published his results, and I think this is, of the original results, this is the one that is published. I just looked at the published paper. It's the beginning of the story, not only of the result I want to present, but also the story of Misha, his first result in dynamical systems. So it's a nice beginning for everything. So for rational maps, we know what the topological entropy is. And the advantage is it's a nice uniform result for all rational maps of the same degree. And the disadvantage is the same. It's the same for all rational maps of the same degree. So there's no way, it cannot distinguish different dynamical systems. So depending on your point of view, you may or may not like this result. Or you like it, but it's helpful for some and not so helpful for other purposes. In any case, there's a way to try to improve it. And the real people, we've heard something about real dynamics and the interplay earlier on. The real people have the dynamical interval. Whenever you have a map, the real quadratics, the graph is like this. And then the interval up to here is invariant. It's a natural invariant subset on which, it's a natural invariant compact subset on which you can also measure the entropy. And for real maps, this is all the more natural thing. And here a lot of study has gone into it. It is monotone with the parameter lambda and unique in the sense that if you have periodic, well, there's a lot of study which I don't want to go into, but here you can do, it's continuous, you can learn quite a bit by not looking at the whole dynamical system on the Riemann sphere, but restricting to an interesting invariant subset. And that's the key advantage. Can we do something like this from the reals also in the complex world? And yes, we can. And this is one of the fundamental ideas. We can argue, was it Thurston or was it before? So he defined core entropy for a post-critically finite polynomial as the topological entropy. Polynomial is a rational map, but you restrict it to an interesting invariant compact subset, which is the Hubbard tree, defined by Doherty and Hubbard. And they exist when you have post-critically finite polynomials. Then there's a natural smallest invariant subset in the Phil-Julia set that connects all the critical points. And it is the same thing. It coincides here with the dynamical interval for the reals in the more natural complex context. So core entropy on the subset, of course, bounded above by the core entropy for the full result, for the full space. But it can be anything between 0 and log t, d. So in principle, it can distinguish different polynomial dynamical systems. And not only can it distinguish it, there are nice studies with beautiful pictures, maybe even videos that I don't show, that just the graph of core entropy records the structure of the underlying parameter space, such as the Mandelbrot set. So you can really recover the Mandelbrot set from entropy graphs. So the nice thing is, if you have a post-critically finite polynomial, which is the classical situation, the tree is a finite tree. You have a finite transition matrix, and the matrix has a leading eigenvalue, and the log of the leading eigenvalue is the core entropy. So that's very nice for a restricted class of maps. And then Thurston asked the question, does this extend continuously to all polynomials of a given degree? And if so, or independently, can you even define this for polynomials that are not post-critically finite, so when you don't have a Hubbard tree? And that became a famous bet between Thurston and Hubbard. Thurston thought probably yes. Hubbard was very skeptical. And well, the bet was decided. I saw Hubbard passing on $20 to Thurston. It was live there. Unfortunately, I didn't make a picture. It was too overwhelmed, but it happened. So for the general question, among the various problems you have to overcome is, even if you connected Julia set, there may not be an invariant Hubbard tree. The Julia set may not be path connected, for instance. And even if you have a Hubbard tree, when the map is post-critically infinite, there is not a finite transition matrix. So how can you read of core entropy in any case? So let me make a little detour through the concept called bi-accessibility dimension, which in some sense is a rather old concept. So you know external angles for polynomials. And I don't want to draw much here. If this is a Julia set, then a point is bi-accessible if two external rays land on the same point from the outside. And the corresponding angles, alpha and alpha prime, are bi-accessible angles in the sense that, well, these two land together jointly. And these angles have been studied. Said, where are you? There has been here you are. There has been quite some story. Stasnunov, Said, Anastunik, that the set of bi-accessible angles has measure 0 on the circle as a subset of the circle. Unless when the Julia set is an interval, then of course every point except the two endpoints is bi-accessible. So it's not joint work, but there were different generalities of this result. But you can go beyond just defining just the measure of the angles. You can look at the subset on the circles and check the dimension of the angles, which are bi-accessible. And then turns out I don't know what the exact source is, like with so many results, that the by accessibility dimension, the dimension of the angles that land in pairs or more than pairs, the dimension of the set on the circle is the same as core entropy, except you rescale, because of course the angles live on a circle, the max is 1, while the dimension is up to log 2. But except for this scaling constant, these are the same things. This is old news. Thurston knew it, but maybe it was known before. And that is a nice way to define core entropy, even in cases when you don't have a Hubbard tree, when it's not post-critically finite. The lamination or the rays are defined in all cases, so you can always study it. There may be an issue. Are there some rays when the Julius is connected, still some rays may not land? Is that an issue or not? But the angles for which the rays don't land are too small. They don't have an effect. This happens too rarely. So this is really a definition that applies for polynomials of all. For all polynomials, all degrees, just when the Julius is connected. And even when it's not connected, you have a couple of broken rays. But other than this, you can even define it in the disconnected case. So this is the same thing shifted up a little bit. We have this definition here, and I'm happy to present a bachelor thesis of Philipp Mehrkamp back in the days that is an extension. We know from the earlier results that the angles have measure 0 unless we have an interval, the accessible angles. In fact, the dimension of the set of angles is less than 1, except when it's an interval. And of course, when the dimension is less than 1, then the one-dimensional measure must be 0. So this is a strict extension to this much earlier result. Philipp later went on for a PhD in Cornell with Gockenheimer, so he was really going to the original people. Gockenheimer will come up a bit later here also. Okay, it is meanwhile old news that core entropy does extend continuously to all quadratic and polynomials and to all polynomials of higher degrees. It may not be known that if you're able to read Chris Penrose's thesis, you'll find a result to the effect in the thesis much earlier. So let me briefly advertise, not so much reading the thesis, if I'm honest, but at least the thesis itself. If you know it's there, and if you have time, you will recover. There is a theorem somehow in Chris Penrose's language, what can I say, that can interpret as exactly this thing here. And that's much before all the others. Interestingly, all these various approaches use different definitions for core entropy in the case that you're not post-critically finite. So in the not so obvious case, there are different definitions which a posteriori must agree, because when the post-critically finite case, it's clear what it should be. And then any continuous function that coincides on a dense set has to coincide everywhere. So much of what I'm saying is in order to prepare for the transcendental situation. Again, this is very, very old news. There are various ways, let's specifically talk about quadratic polynomials, to reconstruct or construct a polynomial Julius set out of minimal combinatorics. So we have, again, the external race here. This is the critical point, the critical value. And all this you can reconstruct out of a single angle that you have at a critical value. So here I've marked the 3 angles. You can choose the 3 because the critical value has 3 choices. This, in Thurston's language, gives a triangle, but in the pre-image is the central gap in this lamination. But really what you need to know is you take any of those. It has, on the circle, you have angle doubling. It has 2 pre-images. So this guy has 1 pre-image here, and well, if some angle has some image under angle doubling, then adding 1/2 gives the same image under angle doubling. So every point has a single pre-image like so we get a diameter. And then this diameter has a pre-image on both sides, and this has a pre-image on both sides. So just knowing the initial angle and taking pre-images just under the condition that they shouldn't cut or cross previous ones is a unique way to essentially construct the full lamination, which is the true topological model of any Julia set if it's locally connected. And if Julia sets are not locally connected, for the spirit of our talk, this will be a problem of the Julia set and not a problem for what we want to do with it. So the short line, two things. One is a single angle allows us to construct the complete topology of the Julia set as it should be. If you know it, you'll know it's beautiful. If you don't know it, it may be a little bit tedious. And I don't want to get into the details, but really it is something in principle easy to see, but it may be a little moment to arrive there if you haven't seen it. So external angle is one thing. From our point of view, the needing sequence is a different concept that is more useful here. So it's the same Julia set with the same critical point, and the critical point disconnects the Julia set into one part containing the critical value. I call this part 1, and this part I call 0. And there are some extra parts here which don't really matter. So this is, if you look at it, there's an ambiguity which is irrelevant. The critical orbit will never be on these bits here. So I can produce from the Julia set an infinite sequence of ones and zeros, just saying the critical value is here on part 1. It goes here, it's on part 1, then it goes somewhere here on part 0. So the needing sequence is 1, 1, 0, and then whatever it is. So this is another term which is coming from real dynamics, but can be naturally extended to the complex world. So the obvious direction from the polynomial to extract the needing sequence, you just look at it and see how it works, and it works easily. But it's less obvious, but it's not really more complicated. If you just know the needing sequence 1, 0, 0, 1, 0, it's coming from an essentially unique, you have to say a little bit about it. It is an essentially unique way to get from the sequence back the full Julia set. And again, this is one of those things which is easy once you see how to do it. But if I try to spend 10 minutes to make it obvious, I'm not sure I will succeed. But let me give it a few minutes. But the main message is don't get worried about details. It is really conceptually easy. So this, now I'm talking about Malte. At the time he was a bachelor student. This goes back to his bachelor thesis a few years ago, before he, like Philip in earlier years, also went on to Cornell. So I will be interested in pre-critical points. Pre-critical points are points on the Julia set or on the Hubbard tree, which after so many iterations land here on the critical point and then on the critical value. They will be of key importance to us for constructing the entropy. And what we need it for is construct or count pre-critical points, and from this construct the core entropy. But it turns out you can construct the whole Hubbard tree. So let me give a hint to how this works. We only know the needing sequence. So then we know from the critical value which sides of the partition it will visit along its orbit. And the sequence of the critical point is just the same. First, it's on the boundary, and after that, it will do what the critical value did the step before. So we know this sequence also. And then we iterate this interval forward, 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 and we know at some point it will go across the critical point. And it will do this as soon as one of the 2 points is on the one side of the critical point and the other is on the other. So we start with an interval, it maps forward, and the moment it crosses the critical point, that is when these 2 sequences differ for the first time. One of the sequences is here, one is there, so there must be a pre-critical point in the middle. So just out of the 2 sequences, we can construct a pre-critical point. And then we split it up, know the new sequences that we had, and each interval we iterate forward. Again, we know the sequences of the endpoints and find pre-critical points. So therefore, if we, just knowing the needing sequence, if we know there's a Hubbard tree, we can construct all pre-critical points in order. But if we don't know it, well, we can still construct all pre-critical points combinatorially between the critical point and critical value when they come and what their itineraries are, their sequences. That means just out of the needing sequence, we can construct this bit of the tree. And then afterwards, the tree is the forward image. We call this the critical path from the critical point to the critical value. So everything you want to know about the critical path, you can get out of the needing sequence. And the tree is the forward union of the critical path. I have more on this on the next slide. But as I said, the details are obvious once you see how they're obvious. And let's get back to core entropy, the concept that we're interested here in this talk. In principle, there are many interpretations, at least in the compact case, and one of them is you take a typical point, whatever that means, and you check the size of the backward orbits. You take the number of pre-images of generation n, and you count how many there are, and then so the number of pre-critical points of generation n, take the log, divide by n, and then the lim sup, that wants to be the core entropy. Well, if you take all pre-critical points on the whole Julia set, you always have 2 to the n pre-critical points, and the entropy will be log 2. So you only want to count the pre-images on the Hubbard tree, at least when that is compact. Well, finite trees are compact. We'll get into this. So the message is out of the needing sequence, we can construct the Julia set, but even without constructing the Julia set, we can compute the core entropy without doing anything. So really naturally, core entropy is a function just of needing sequence. So maybe I should have flipped the slides, because this is what I said. The first step is critical value, the needing sequence, then the sequence of the critical point. Critical path connects the critical point to the critical value. And all the pre-critical points here, there's a very simple algorithm, which I just went through. It's just the combinatorics. The Hubbard tree is the union of those. And now what I should point out here is it's just this pretty much arbitrary sequence, needing sequence of zeros and ones. So far, Hubbard trees were defined only for post-critically finite polynomials. But this definition has no such restriction. So for one, just knowing the needing sequence, you can compute the core entropy. But in fact, you can always construct a Hubbard tree, or a tree that is equal to the Hubbard tree when the Hubbard tree exists. But it's quite possible that the critical orbit is infinite. It may be that the Julia set is not path connected, so there is no Hubbard tree in the classical sense. Well, sometimes the Julia set is path connected, and you can still connect the critical orbits in the Julia set. But if it's not path connected, then what do? Well, again, for us, that's a problem of the Julia set. Let it be path connected or not, that's its problem. We know the needing sequence, and out of this, we have everything we want. And then, of course, interesting question is, how can you tell from the needing sequence what the actual topology of the Julia set is? Which is a difficult question that for now we are simply ignoring. It's always the nice thing you do with difficult things. Just ignore it, move on to more productive ways. So suddenly we have a nice definition out of doing nothing for core entropy that works even when the Julia set doesn't exist. And it works even more generally when the polynomial doesn't exist. So there are needing sequences, just random sequences between 0 and 1, many of which occur as needing sequences of quadratic polynomials, and others don't. So there was an old paper with Hank Boyne in which we classify which ones exist or not, about it. There's 80% chance for random sequence to realize. But there's a positive probability that they just don't come up, don't exist at all in complex dynamics. Doesn't matter. The needing sequence exists, core entropy exists, and it's continuous. Everything is nice. So in the Julia set, path connected or not, doesn't even exist. We don't need it. So I really like Malte's idea to construct everything out of nothing, ignoring all the difficulties. And in particular, I spent a lot of time discussing first with Henk and then with a former PhD student, Alex Kaffel, how to construct Hubbard trees just out of the needing sequence in the simplest possible case when the needing sequence is periodic. We could do it, that must be true. We worked hard for it, knowing it must work. We did it, and it took a long time. And here Malte has a very simple definition, which needs nothing, and it's just there, showing us just how much work we spent for, well, 20 years earlier. I mean, that's progress in the future. Okay, so this is a nice constructor. We're just out of elementary combinatorics to get out of it, everything out of it without worrying about existence or topological problems. So what we do is, for every external angle, we can construct the quadratic polynomial or the needing sequence, and then core entropy, and even for needing sequences that don't come from angles. And as we said earlier, this map is continuous in the quadratic case and beyond. And then people had asked 10, 12, 15 years ago, how continuous is it? What is the modulus of continuity? And there have been quite some discussion in particular, is it Hölder continuous? Again, this goes back to work of Guggenheimer when he was a PhD student. One of his old papers in the real dynamics he had shown that in certain real settings, the natural modulus is really Hölder continuity, with Hölder exponent being the entropy at the point. So that was a natural conjecture. I don't know who phrased it all, this map, angle to needing sequence is Hölder continuous, and the Hölder exponent should be the entropy, again, scaled by log of the degree. And the exponent, well, is it the exact exponent? Is it the exponent up to epsilon? Well, you can play with it like often with Hölder. There's a minus epsilon in it. And there has been quite some work on this. So I talked to Guggenheimer a few weeks ago, asked him what was your motivation, and he said, well, it was natural and in the air at the time. And he quoted some work of Anosov in a very different context. And it was part of a conjecture which in the end didn't work, but it was, he said, very natural. It was just the thing to do. It is the right thing to look at. And in fact, it is true. It has been shown by Giulio Ciozzo along the real slice of the Mandelbrot set. And so Wolf is here, I'm happy. It has been shown for certain post-critically finite endpoints in the Mandelbrot set. And there have been at least 2 announcements 12, 15 years ago for the full conjecture, which, as far as I know, have never been substantiated. And now I'm happy to present a result, again, work with Malte, that this conjecture is true for all angles that are non-recurrent, with the additional condition, you know, Malte can construct the Hubbard trees no matter what, and in many cases, the trees are infinite trees. Well, that happens only for certain endpoints out at the Mandelbrot set. And that's an extra condition we have to put in if the tree happens to be finite, so we are not at those endpoints in the Mandelbrot set. In the non-recurrent case, then this conjecture is true. And I think this is as much as I wanted to say about core entropy for rational maps. And now let's remove the question mark from the title and go to the transcendental world. And so, both in the polynomial and in the transcendental case, I start with quoting the same result that Han Peters stated. And this time, I think our references coincide. So transcendental entire functions always have infinite topological entropy. This is a nice result. It has the same advantages as Ljubich's result and the same, well, creates the same wishes, let me put it this way. It's constant for all transcendental maps, so it does not distinguish any transcendental maps in terms of entropy. So, and then the question is, how do we extend core entropy? Do we find whatever a good definition for core entropy to the transcendental setting? So that, well, of course, the infinite value is always there, but at least for maps of finite type, so when we have finitely many singular values, that the value of the entropy should be as finite as possible in order to really meaningfully distinguish the maps. Well, and now we have a lot of problems. So looking at invariant subsets of the Julia set. So let me show you famous pictures of I have some nice pictures here. This is the Julia set of a typical transcendental entire function. It's the full complex plane. So the Julia set itself doesn't show you nice invariant subsets. So how can you produce invariant subsets like here in the real case, for which you can produce good definitions of core entropy? So Hubbard trees do not exist. I have a slide afterwards. Then let's look at bi-accessibility dimension, which worked for all polynomials. But again, there is no natural measure on external angles, whatever they are, external addresses. So that approach doesn't work either. So the path to the solution is, remember, ignore all the topological issues, just work on the combinatorial world. And the goal of this talk in the 20 minutes or so that I still have is to walk towards a reasonable definition of core entropy in the transcendental world, which is a paper in progress, again, with Malte. So one of the problems is Hubbard trees don't exist. And let me show you why. This is the bachelor thesis of Michael Roesch, another bachelor thesis, 2000, when was it? 15 or thereabouts. This is a post-singularly preperiodic exponential map. So in some sense, this is the easiest transcendental entire function to look at. The Julia set is here is everything. So we have the singular value, which is here, I pi, z maps to I pi exponential of z. We have the singular value, and we know there is a dynamic ray that lands at the singular value. Dynamic ray is just it's a curve of points that converge to infinity, and there's a unique such curve from infinity out to the singular value. And all these points in iteration will go to infinity. So if you have a curve that goes to the singular value, then under the exponential, the pre-image is a countable set of curves like this, parallel to each other at distance 2 pi, which goes somehow to minus infinity. So this gray here indicates we are close to minus infinity there. So they cut up the complex plane into parallel strips of height 2 pi. And the cutting is by points that converge to infinity. So the key issue is the Julia set, or the post-critically finite map. The singular orbit cannot be in a single such strip because, well, the critical value cannot be periodic. There is no singular value is 0, and the 0 is omitted. So it must be pre-periodic. That means some point has 2 pre-images. But 2 pre-images for the same point are a distance 2 pi I apart, or a multiple of 2 pi I. So they must be in different strips. Now you want an invariant compact tree that connects different strips, so it must go through the partition boundary. But the partition boundary consists of escaping points. And it's impossible to have something compact invariant that contains an escaping point which goes off to infinity. So there is no Hubbard tree for any post-singularly finite exponential map, and for many more transcendental maps in general. So, and the main result of Michael Roesch's bachelor thesis was, for one, there are no Hubbard trees, and then to construct these Hubbard trees. And how do you construct something that doesn't exist? You relax the conditions. So, and then this went on to David Fang's PhD thesis for all transcendental maps that are post-singularly finite. You have, well, you don't have an invariant Hubbard tree. We just proved they don't always exist. Sometimes they do, but there's always a homotopy Hubbard tree. So you remember in all of Thurston theory, all the data are given up to homotopy. So it's natural to do the same thing, construct the trees only up to homotopy. So homotopy Hubbard tree is a finite tree that connects the post-singular points like the actual Hubbard tree. It can have periodic or pre-periodic branch points that are not on the post-singular set, again, like for polynomials. But it's a finite tree, the endpoints are in the singular orbit. And as a finite tree, there is a finite transition matrix. Every edge is defined only up to homotopy, but the edge knows which endpoints it wants to connect. And that's enough so that this edge maps homomorphically because there's no critical point. If there were a critical point between, it would be part of the tree structure. So it maps homomorphically up to homotopy to an image edge. And that means out of this homotopy trees, you can again construct a finite transition matrix. And in the usual way, you get a leading eigenvalue, and the log of that is the core entropy. So that is one is not the easiest, but one natural way to construct core entropy for all post-singularly finite transcendental entire functions. So I have this only in this sentence. Before I say only, I'm very proud of the result. It works for all entire functions, no restrictions at all, except they be post-singularly finite, which implies they have only finitely many singular values, so the matter is to be finite type. No further restriction on this. So we have the homotopy Hubbard trees, we have the coentropy, and then the question, like for polynomials, is what can we do in order to extend the result in greater generality and see continuity or whatever issues that come up. And the world here is more rich. Things can be more unbounded and discontinuous. So let me mention a few results that have been obtained for special cases that could gauge our intuition as prototypical results. First is, if you just look at exponential maps, lambda times the complex exponential function, coentropy is always at most log 2, which has been a bit surprising to some people. I should say the same is true for unique critical polynomials of type z to the d plus c. So for them, they have the same upper bound, not log d, but log 2. I want to convince you why this is natural, even though it's not what some people have expected. For cosine maps, on the other hand, lambda multiplied by the complex cosine function, core entropy is unbounded. So there's no uniform bound on the whole parameter space. Worse than that, there is every map lambda star times cosine. If you take an arbitrary map in the bifurcation locus, it is the limit of post-critically finite cosine maps, so that along the sequence, core entropy tends to infinity. So that every bifurcation point is a limit with value infinity. So if it wanted to be, the function core entropy wanted to be continuous, it had to be infinite on the bifurcation locus. But the bifurcation locus contains post-critically finite maps with finite entropy. So core entropy for cosine maps is intrinsically not continuous in any reasonable way. So here we have a result about non-continuity, and we have a result about continuity. Roma and Bernhard Reinke sitting there. If you restrict to those maps that have bounded combinatorics, then you can use the results from the polynomial or the methods from the polynomial theory and get a continuity result on this restricted subspace. So why can argue whether exponential or cosine are the simpler transcendental maps, why in one case exponential is very nicely behaved and cosine is so much more weird or interesting. The exponential has a unique singular value, and it has no pre-image, the singular value is omitted, but somehow morally near minus infinity, there is a critical point with perhaps infinitely many branches out at infinity. We'll get to see this on the next slide. On the other hand, cosine has two singular values, 1 and -1, standard normalization. And it has countably many critical points of the simplest possible type. And the pre-images, the single critical point versus arbitrarily many, that will make the difference, and we'll see this in a moment. So let's connect back to leading sequences of polynomials, which exist for all the unit criticals, and they exist for the exponentials. It's the same picture like this, where you have these sequences are sequences over the integers, not just two symbols. Well, the degree is infinite, so you need infinitely many symbols. Just the fundamental strips like so are labeled by the integers. And then the needing sequence is you look at the critical value and see which strips it visits in order, and that gives you an infinite sequence. And now Malte does the same thing like for unit critical polynomials. Just out of the needing sequence, he constructs an invariant tree, a unique invariant tree that models the dynamics. You just need to know the needing sequence. Periodic, pre-periodic, or not periodic, doesn't matter. You always get a unique tree. It may not be a finite tree. Certainly, I'll have an example on the next slide or so, which shows that the tree can be infinitely many branch points, each with infinite order. So the tree can be very complicated, but it's a naturally defined tree. It is certainly not realized as the subset of the complex plane because, well, we showed they don't exist. And this branch point at infinity, well, is at infinity. But hey, all these are problems of the complex plane and whatever. The tree exists and it records the dynamics of the exponential map. And it's the same construction that he had for quadratic polynomials that works for exponentials. So there is a tree, and on the tree, well, we'll read off the needing sequence eventually. But first, we just have a nice tree that describes the dynamics. And yes, so this tree has a single critical point. And so it's an eraser, yes. So core entropy, in a way, tells you how many combinatorially different orbits you have in your dynamical system. So the typical Hubbard tree for an exponential, here's the critical point with many branches. It has pre-images, whatever. But the point is, it's on each complementary parts with the critical point removed. And now I talk about the critical point for the tree. It's not a critical point for the complex exponential map, but it doesn't matter. So the map is injective on each of those components. So if you want to really, you should look at it from the point of view of an interval. You start and we'll define this. So you have an interval. It maps forward homomorphically. So the forward image gives you no new information. It maps forward homomorphically. And it may map forward over the critical point. And then it cuts into two parts. And you can continue with the two parts. When it happens, you can record from the needing sequence. And so the number of parts that you have to iterate injectively can at most grow by a factor of 2 in every step. So after n steps, the number of parts is at most 2 to the n. Well, log is, and take the log, divide by n. So really from this point of view, it's very natural that the core entropy is at most log 2 for all exponentials, at most. The tree, as I said, you always, so let's try to do this in general. I have almost 10 minutes. Let me see it quickly. If a transcendental entire function, suppose first we had a Hubbard tree, then work with it, and then see what we can do without using the Hubbard tree in the first place. The Hubbard tree can naturally you can have a homotopy tree. The map doesn't have to be post-singularly finite. The tree may be infinite. It may fail to be compact. All this doesn't really matter. And then we try to define the entropy on the tree and then replace the tree by combinatorics. So some natural setup would be just to define core entropy as topological entropy on that tree. which is a subtle issue, as the authors of Miriam, Hahn-Peters, and others can confirm. If the tree is non-compact, then this is going to be annoying. But implicitly, it's lurking there. And that's equivalent to the first definition. It's the exponential growth rate of pre-critical points on the tree. So points that eventually map to the critical points. It's one definition. Second definition, you don't look at the full tree, you just look at a single interval, such as this one. You iterate it and count pre-critical points on that interval and take the supremum over any such intervals. And the third is you just take, this is a huge collection of intervals, you just take intervals between singular values and its image and then take the sup over those. So there will only be finitely many intervals to check here. The bottom line will be these two definitions are the same. This may be more conceptual. This is simpler to check. And this one is no good. Why is that one no good? This is one of Malte's favorite examples. It's an exponential map with a nicely structured needing sequence. And if you just count, I could go into it. Essentially, this is the complete proof, but maybe I'll skip that. Counting the number of pre-critical point and defining the entropy that way gives infinite entropy for an exponential, while we want it to be at most log 2. In fact, the number of pre-critical points itself is already infinite for every step. So you have infinitely many pre-critical points of every level, take log of infinity, which is infinity, divide by n, take the lim sup, doesn't help, it's infinite. So there are cases like this when the entropy is too big. So you shouldn't look at the full tree because it's not compact, and then you're in trouble. The other two definitions that I mentioned before give the same results. This is more natural, and this is easier to check, and when they're the same thing. So this is a definition that we propose. Exponential growth rate of pre-critical points mapping to any critical point on the tree, and then you restrict it to an interval to any singular value in its image. That way, you compute a number that in general is finite and gives you a good description for the dynamical complexity of the maps. And here's a basic bound on this. If you have on the tree at most k linearly ordered critical points or generalized critical points, so there may be infinitely many on the full tree, but only finitely many linearly ordered, then core entropy above is bounded by log of k plus 1. Well, take the max. Take the max. Yeah, some critical value could be very tame, and the other do the interesting things. Take the max, but the whole definition really makes sense only for finite type maps and finitely many singular values, so finitely many intervals to check, which is much better. We want to get away from infinity. Thank you. So once you see what's going on, it's very obvious that intervals can get cut into at most k plus 1 parts in every step. And that explains, but I shouldn't explain it. For instance, the double exponential has infinitely many critical points. There's main critical point here, and then there could be critical points in all branches. So there are infinitely many critical points all the way over, but at most 3 are aligned. So the core entropy is at most log of 4, which is twice that for the exponential, which is what you would expect. And for cosine maps, you have critical points as many as you want, all aligned. So there is no natural bound, and the entropy can be as big as it wants. We have kappa-affine, a certain definition for kappa-affine entire functions. That is when something, the tree has only finitely many endpoints, in the sense that the kappa post-singularity points and all the other post-singular points are between those finitely many points. So then we really have a finite tree. And in those cases, the function has finite core entropy. And here you can use all three definitions that I mentioned, including the one with entropy on the full tree that I excluded here with this kind of infinite trees. Again, I'm happy to take questions why this is so. It's not very hard, but I want to stop on time. So this is the last slide, and I want to spend a minute or two on this. So far, I've used, intuitive at least, trees for transcendental maps. Well, the whole bottom line is trees don't exist, and if they exist, we don't want them. So really, like for quadratic polynomials, a single angle or a single sequence is enough. For all posting, you take a finite type entire map. It may be postingly finite or not. And we want to define a minimal combinatorics, like for the laminations, that determines everything. So we have an entropy defining set of combinatorics. How do we get there? One special case, if the escaping points are organized in the form of dynamic rays, curves going to infinity, such that a singular value lands at each singular value, then we take those rays that describes your singular value. Well, and then, so this is a nice condition, and now you throw away everything. The landing is not necessary. The ray doesn't have to land. It just has to accumulate in a combinatorial way so that the singular value is associated to the external angle, which is really just the external address. External address is the proper name, the angle of this ray somehow. It doesn't have to land. And you don't have to have rays. Some transcendental maps have rays. Some just have very wiggly objects that have no path components that we call filaments. All doesn't matter. You really just want to have the external address or the external angle. And then if you have one ray that lands at a critical value or singular value, take whichever pre-image is 2 or 3 you need, and their angles. This determines the combinatorics. Really, this combinatoric set is all you need in order to construct the combinatorics out of which you get the core entropy, even when the topology is complicated. So 51 minutes. Thank you very much.
I'm wondering if all the story can be refined to the level of the core measure of maximal entropy. So somehow you put on your Hubbard tree, say for Pascale finite polynomial, you put on the Hubbard tree the Markov measure of maximal entropy, and you can then try to extend it as a continuous functional to all polynomials of a given degree. And so can it be refined in this way? Can it be done in this way? In fact, one number instead of number entropy just considers the whole measure as a functional.
Maite, when you hear us, you know what to do. Thank you for the suggestion.
So you have not considered it.
I haven't thought about it, no,
So
but
it could be implicitly in this discussion.
So it's very worthwhile looking into, and we will. But for now, I just take the homework.
Okay, next time.
Other questions?
Caroline. Oh.
Thank you. How does your getting a tree out of the needing sequence distinguish like conjugate maps or?
It doesn't, and it doesn't have to.
Oh, okay.
They're really the same.
Okay.
I mean, they're topologically conjugate without embedding. So it's really naturally the same map with the same every properties.
Okay.
It's just the difference is in the embedding, which has no bearing on the entropy.
Cool. Thank you.